I think I will start the class. We will see if somebody can join later. And anyways, this video will be recorded. So first I will share the screen. I think I am sharing the screen and everything can be visualized. Hello.
Yes, sir.
Yeah. Thanks for joining the class, and we'll wait. I think we'll start the class because it's already 6-7. If somebody join, then they may join. Okay.
Okay.
Okay. Fine. One second. My mic is off. Okay. So can you see my screen?
Yes,
Is it visible? The
sir.
PPT. Hello.
Yes, sir, it is visible.
Yeah. Okay. Fine. So as of now, we have completed the 3 weeks course, and 3 weeks TA classes. And in the 3 weeks, I'll glance through the 3 weeks classes for the first 10 minutes, and then we'll go through the week 4 TA classes. And it's been as it was the last week's class, so I will continue that class. So as we all know that this is the problem solving session for the thermodynamics for biological systems, classical and statistical aspect by myself, Karnataka Ganesh Reddy I am from IIT Patna. One second. Yeah. So we all know that what is system and how the system surroundings are differentiated by the boundary. And once you all know this, and then we have the 3 different types of systems. One is open, closed, and isolated. Out of which, and we know that how we can describe the say I have open system or closed system or isolated system. And we all know that how can we describe the system, say suppose by microscopic properties. Basically we will develop by microscopic properties such as pressure, temperature, volume, and so on. Further, if you there are 2 types of thermodynamics which we will discuss. One is the classical, and later part is statistical, where the classical deals with the microscopic approach, and the statistical deals with the microscopic approach, where the microscopic tends to say that movement of a particle and the vibrational force, rotational force, etc., etc. And the microscopic, as we all know, that deals with the temperature, pressure, and chemical composition. Okay. Then we all know that the different laws of thermodynamics and which it deals with. It starts with the zeroth law to third law, and zeroth law deals with the temperature, and third law deals with the numerical values of the entropy. And the best example of thermodynamics which was used in the movies like Tenant. And then we all know that when can you say the equilibrium was at microscopic level, the system attain a state where it appears to be static, and at microscopic point it remains constant and uniform. Say suppose if I'm at 300 Celsius and the 250 Celsius, they both can be at the equilibrium of the same system. So that's what it was mentioned as equilibrium. So once the equilibrium is done, and once we know that what are the systems, we have different types of systems again. One is homogeneous mixture, and another one is heterogeneous. Say the best example of homogeneous is the coffee in thermos, mocktails, gas mixtures, dry air, where you can see a number of particles revolving together without any disturbance. And the heterogeneous is like we'll have a system with the 2 or more distinct phases. I will explain what do you mean by phases in the later part, which we discussed earlier also. Once I started heterogeneous, we have the glass of water and ice. Say suppose the human body, where we have the different types of cells all together, and a mixture of water and oil, where there are 2 different entities, and the boiling water, where we have the liquid phase and the vapor phase. So when we have the 2 different phases, we will call it the heterogeneous phase. And if we have all different types, suppose if I take the coffee, there will be a water, there will be a coffee powder, and there will be some sugar molecules and all the things. But still it will be like all in the same format, so it will be like a homogeneous mixture. So once you know homogeneous mixture, heterogeneous mixture, you have the system, open system or closed system or isolated systems. And then you have what you say the properties which you are defining. So once you know this, this is once you know this, we have the variable, state variable and path variable. Say suppose if I'm moving from point A to point B, say suppose if I'm moving from point Delhi to Kanyakumari, I will consider only the starting point Delhi and then Kanyakumari. Then I will find out the differences in the energies. I won't care about whether I have taken the train route or the flight route or what is the path I have taken. So if I not get focusing more on the path which I have taken, then it is called as a state variables. And if I focus more on the path variables, we will known as path variables. So that's what I mentioned it in the diagram here, the side diagram. So once this is done, we have the zeroth law. We all know that the Celsius scale thermometer are designed from thermodynamic laws. It says that when we have the hot water and cold water, basically the zeroth law deals with the temperature, where you can see, suppose if I given the second example, where the heat is transferred from A to B and B to C and C to A. If I say that A is a higher what you call high temperature body, B is a little bit like medium, and C is a cold body, then the heat will be transferred from as I mentioned it here, it will be transferred from A to B. One second, yeah, it will transfer from A to B, and A to C, and B to C. That's what we have discussed already. From the thermodynamics law, zeroth law, we can say that the heat is transferred from the hot body to the cold body, not in the vice versa direction. And based upon this principle, and we can why the zeroth law is inverted, or what is the useful of the zeroth law was, you can measure the temperature difference between the 2 points. That's where the zeroth law has been used by Celsius, Fahrenheit, and Kelvin, and so on people, to give us the thermodynamic scale. Say suppose you can use the identify the temperature difference. We can take one neutral point. Say assume that you are the neutral point and you are moving from, say at this time you are moving to the northern part of India, you will feel the cold, and if you come to the southern part of India, you will feel the hot. So basically you act as a thermometer here to distinguish the two different entities. As your temperature, we consider you as a stable body, and the raise in the temperature of you, either by, say suppose you got the fever or you got the cold, or sometimes when you see, if you see any uh, steel manufacturing process, you can see the changes in the heat on the, so the color of heat goes from the red to the normal brownish black. So these all are the major examples or major inventions carried throughout the zeroth law. So from this, the basis of Celsius scale, or Celsius scale was done taken by the boiling point of water as 0 degree and water degree Celsius, and Fahrenheit has taken the basis point as the human body temperature. And then we have the Kelvin scale, when, so this is the Kelvin scale. So yeah, and then once you got the Kelvin scale, we have the PV equal to RT gas for ideal gas law. That is the theorem. So basically you need to remember the one thing, if you take any, there is the equation of state which we will talk more about in the thermodynamics. What does the equation of state deals with? That was, say suppose if I given a major flask, saying that okay, I have this flask and we need to find out the, say what is the, say suppose I have given any system, if I give, one second, if I say suppose, I'm just drawing it here something, I'm given a container, and where I have given the three boxes, where there is a B, C type. We can understand that how much C is compressed, how much B is expanded, or how much A is has been gone through. So based upon these all properties, we will calculate the equation of state by using the basic microscopic properties, which are VPT. That's if you see that there is the equation saying that, if you see it here, it is saying that V equal to V as a function of number of molecules, P and temperature. If it is given as a only single system, then we have the major formulas is given by van der Waals, and I will explain the same van der Waals in the later part also. So yeah, once you have the basic definition of equation of state, then we have the disorganized form of, if I consider about the first law, where we have the energy is in disorganized form as internal energy, which can be moved from one part to another part, and it's all based upon the experimental observation. As we all know, the thermodynamics laws has no proof, but once you have taken a thermodynamics law as a theorem, and if you can solve it with any example, it will be applicable. So that's why we says that it is verified through the large number of experimental observation, and we have additional 4 laws. You can it's not 4 laws, with the 4 laws we have additional postulates which easily can describe thermodynamic states. Initially I said that we have only volume, pressure and temperature, but along with that we can use enthalpy, internal energy, Helmholtz energy, Gibbs free energy, which we will discuss more about in the later part of the class. And these are the some examples which we discuss, and this is the work, how the work is related and all those things. So yeah, now we will go to the class. So you all know, right, for closed system what we have done was, so basically whatever we have dealt before, it's in the two forms. One is like closed system, another one is open system. If we are talking about the closed system, where there is no mutual transfer of mass between the outer and inner system surrounding, so that's why whatever you are doing, there won't be any number of molecule terms. So if I go through here, there is no term for the number of molecules. Is that's the same thing. If you come to the open system, we have the number of molecules. Number of molecules in the sense, as I said earlier, given in the container. One second. Yeah, given in the container, say suppose we have the two different types of molecules, one is like suppose two different types of gases, how much compression is happening and how much internal energy has been transferred. So that's what we will discuss in the open systems or in the closed system. So in the open system, here we have the thin barrier between the two systems. So once we have this, we will go and then we have these relations, Maxwell relation and all, and I have given the work some what do you call the how we can derive the Maxwell relations, and there is a small PDF I have posted in the drive folder. You can see it regarding the how Maxwell relation is used, how the reciprocation formulas are being used. As I said, we have I have mentioned it here, df equal to adx. If you have some equation f as a function of x y z, and how can we differentiate to get the enthalpy or Helmholtz and Gift energy. So that's been given nicely in the outlet. So if you want, you can go through that drive file which has been uploaded in the drive. So once we have this, and then the phase rule, as we discussed initially, the homogeneous or heterogeneous, it all comes from this. There is the equation f equal to minus pi plus n, where f is the degrees of freedom, pi is the number of phases, and n is number of chemical species. I think we already discussed, and it is very easy topic. This is suppose the triple point. If you take triple point, why this is important was, if you take triple point, where it exists in the only one condition, where it exists in the solid, liquid, and gaseous form. So suppose in the triple form, if you say it is 2, the number of phases is 3, and the water number of chemical species is 1, that is water molecule. So now the degree of freedom is 0. It means what does it say? The degree of 0 means how many parameters you can change such that you can study the properties. So for that triple point, you can't even change the one point to study that triple point and another point. So that's why you need to understand the triple point at only exactly at one point. And if you say about, if you take the system of steam and liquid water, say suppose we have two different phases, one is steam and liquid. So here at that time it will be 2 minus 2 plus 1, it will be 1. So now f equal to 1, what does it say was the degrees of freedom is 1. So what does it implicate was, we can change either temperature or pressure. As I mentioned it here, with one property you can change, by keeping one property as a constant, you can change one microscopic property, and then you can understand the, okay, what is the variation happening on to the system based upon these values. And you can say that sometimes you will get the as you can see, sometimes you will get zero, invariant, univariant, bivariant by further examples. So this is the three examples which will give different types of systems. Once the phase rule was done, these are the examples which related to the things. And then as we all know that if you take any, if you talk about any enthalpy or any Gibbs energy, the relation is very complex. So suppose if somebody asks that, if somebody says that in the lab scale or in the experimental, they say that I have the values of temperature and pressure, can you give me the values for enthalpy or entropy? So then you need to understand that how can we converted the given the what we know the form of entropy or enthalpy to the what you call desired form of temperature and pressure. That's what we discussed in the last classes. And this is a very important term, so you need to understand that. If you don't understand that, there is a two forms of doing it. One is Jacobian way and another one is the normal way. So I think I explained both the cases in the last classes. So yeah, I think so. This is the Maxwell way, where you can see the diagram and with the plus or minus signs. If you go to the previous videos, you can understand how to do the Maxwell relations. So once Maxwell relation is done, you can use the Jacobian, which is the easiest one, to figure out how to do the T comma P and T comma P for the entropy and enthalpy. So now chemical potential, this will be again will be discussed in the later part of the class. I think in the fifth week or sixth week classes. So this is I have given some basic outlet, and I will explain you further like extension form of it today also in the class. So yeah, so once we have, so whatever we have discussed previously, it is for the closed systems. Now we have the open systems, where we will talk about the how the mass flow rate is in. Say suppose I have taken flask of water which is cool water, and I open the lid, and what is happening was there is a transfer of fluids from the air from the outer to inner and inner to outer. So that's what we are talking about in the open systems. So how can the compressibility factor will occur and everything in systems in the open law. And these are the, say suppose if I take any open system, there will be a loss of mass conserved and energy loss will be conserved. So that's what we discussed here. So once this is done, yeah, so this is another example of some week 3 classes, I think week 3. So these all are the like the easiest way of derivation I am explained. So yeah, so now for this class we'll go in the last class I didn't explain how we are doing the volume estimation. say suppose this is of the I think week 3 end part or week 4 starting part. Why we need to do the say suppose volume estimation. I think this will be the easy one. We all know that I think if you have gone through the SERS videos, we have the Redlich-Kwong equation, which is the updated version of the van der Waal, where we will include the temperature condition, as we have know that to get the more better appropriate results. And in the volume estimation, how can we do the volume estimation was, one second. So we all know the equation of so this is the equation, and we need to find out the volume. Say suppose volume, as you can see there is one for example question also. So for that what I can do was I will take the denominators out to get the equal denominator. So I will divide all the equation with this term, so that we will get so now what we will get was this one will get cancelled, and this one will get cancelled. So it will be PV V square minus V square equal to RT V square plus VB minus A divided by V minus V into T to the power 0.5. So then I will make this equation as PV cube minus PV B square equal to RT V square plus RT VB minus AV whole to the power T to the power 0.5 plus AV square root of T. Now if I make this equation, V square plus RTVB minus AV to the power T to the power 0.5 plus AV to the power T to the 0.5. Now I will bring all the equations to the one side. So then this equation will be in the form of cubic equation. Just try to understand that we are making the equation in the form of cubic, so that it will be easy for us. So it is a cubic equation where we can use V equal to what you can write minus of. So now to make it in the cubic equation, we will divide all the equation with respect to P. So then we will get minus of V cube minus RT by P into V square plus minus AV by root T divided by A into T to the power 0.5 minus RTB minus PB square, not PB square. So there will be here also there will be P, here also there will be P, I think. Yeah, here also there will be P, here there will be no P, it will be B square. So this is the volume estimation equation which we will get it. So this is the way how we will get it. In the tutorial, in the classes there is no explanation of how we will get this equation. So that's why I derived the equation here. And basically using on this equation, we will say that okay, initially there is this the given volume, pressure and temperature is this, and while consider the experiment and how much expansion is happened, then we can do this by using trial and error method, and we can get the approximate value. So once we know the volume estimation, then we will go to the real equation of state. So as we discussed, I think the underlying concept from the starting what we are discussing was whatever we are discussing is for the ideal gases where the volume is negligible. Okay, but if you take any real gases where we have multi components and where there will be like attraction or the repulsion or there is intact with the walls, then we need to get the one equation. So based upon that we have different virial equation. One says that there is a compressibility factor, and virial equation there is a cubic equation. Then comes the van der Waal, or the previously which we discussed, the quark equation, Redlich-Quark equation. So what we can understand was, so suppose if I take the any equation as a, this is the basic one, f equal function of v comma p comma t, and there is a power law. You need to understand the power. There is a power law in mathematics where it says that when if you take any, if you take the graph, if you have the phase diagram, if you go for the isotherm, the graph goes like this. It means as v increases, p decreases. So I written the same thing in the different form. If you take the graph of PV isotherm curve, we can see the saturated vapor curve where p increases when v decreases. So I written the vice versa of this, where v increases, p decreases. So I mean this, the graph will go morely like this. Yeah, so that's why, but as PV as a function of t, so this is actually taken under the isotherm case. So but as a function of t, there is a minimal change. So if I take individual values p comma v, there will be a huge changes. Suppose as p increases, it increases in a huge way. But how to say it, when I have taken the PV as a function of t, the values are minimum. So then at that case you can use the power law. Suppose what does the power law discuss was, I will explain it in the further way. I will explain it in the good way. So suppose a comma b and the 100, it is 100, then ab is 100. Now this is, say suppose if I go to the 48, if it is 2, there will be 96. And then if I take this as 4, if I take 16 4 is 64, 4 8 is 32, 19 9 4 is 36, 20 80 24. Then it is discussed to 24, 4 4 is 12, 92. Then if I take 8, this will go 16 is 48, 5 is 40. If I take this, it will be like 12, 96. 16, 96, sorry, 96. So if you can see it here, b is gradually increasing and a is drastically decreasing. But if I do ab, even though if a is going from 100 to 12, there won't be any much differences from 100 to 96. You can see that outcome, 100 to 96. But in the same cases, it is going from 1 to 100, 8 is also 96. So the gradual increase in b has much effect on the ab compared to a. So that's why then at that time we can use the power law, which says that then ab can be written as function of b to the power n. This is what power law discussed in the mathematics. Based upon this equation, we have written PV as a function of over to the n series. So which will give the equation of this PV equal to as power series, we have written the power PV equal to a plus bp plus cp square and so on. And now we are assuming that b equal to ab dash and c equal to ac dash. I mean we are just changing notation such that we will get the a as common. So now if I remove the a, now here a acts as a constant, and all these functions whatever there is a constant, suppose b dash comma c dash then d dash, this all are dependent on the function of t. Okay, but a is not dependent on the any function, so that's why a is not dependent. So we have this equation, and at any we have the isotherm condition. It means at the constant temperature, say suppose there is no changes, then this all terms will become 0. So then we have only PV equal to a. As we all know, for the ideal gases, PV equal to RT. So which says that a equal to RT. That's what I mentioned it here, a equal to RT. If I take any compressibility factor, we know that the compressibility factor which we discussed was initially the compressibility factor to design more the repulsion and attraction between the molecules, they have decided the compressibility factor as V by V ideal. We know that V ideal is nothing but Z equal to V ideal is nothing but RT by P. PV equal to RT, so then it will become PV RT. Don't confuse this with ideal gas volume. This is not ideal gas volume. So that's what Z equal to PV RT. So then PV equal to A into 1 plus this equation has been converted to PV equal to as PV equal to, you can see, yeah, here A equal to RT, and then it will convert into this. So you have any doubts regarding this, how this variable equation has been carried out, then I will explain it again. If you have no doubts, then I will go further in the variable equations. So once we know the virial equations, and then we have the compressibility factor. So we all know that what is the compressibility factor equation primarily involves the critical. See, if I say Z equal to PV by RT, where it mostly deals with the critical pressure and critical temperature, the value the values are nearly exact for the simple fluids such as argon. So basically why we are doing this was, if you have any ideal gases, we have the PV equal to RT equation, which will be helpful for all the gases. But when we have the ideal real gases where there will be what do you call attraction or repulsion, that's when we are coming with the new topic, two new terms called as compressibility factor or virial equation or the cubic equations. So in that also there is another catchy loophole, says that okay, you have developed one compressibility factor, but that is shown good for only for the simple fluids such as argon, krypton, xenon, which are noble gases. But for if you go for the more complex fluids, the values deviate significantly. So based upon this observation, the Pitzer developed an equation and coined it as a eccentric factor. So what he has done was, so basically what we are doing was, so initially the equation also Z is dependent on the critical temperature and pressure. Now what he has done was, he has derived a new equation, says that okay, the slope of partial pressure, so the slope of the reduced pressure, I will discuss the reduced pressure. So reduced pressure, I think this is also explained in the class, reduced pressure or reduced temperature, which deals with the TR equal to T divided by T critical, and PR is P divided by P critical. So why we will do this was, at the reduced pressure or the reduced values, all the components, that's what the initial assumption was, at the reduced values all the properties of any given solid will be same, any given fluid will be same. Based upon that, he says that eccentric factor for a pure chemical species is defined with reference to its vapor pressure, and you can see that. So once they plotted the graph for as a, so this is basically nothing but a dy by dx equal to m slope, yes. So they found one graph, says that, which passes through the line, this line. So they taken this line as a standard curve line. From that they said that okay, if you have any compressibility factor W, what we can do was, we can find out how well of simple fluid minus the desired fluid. As we all know that by keeping the temperature as a constant at TR equal to 0.7, sorry 0.7, so we all know that simple fluid value is -1, so that's why W equal to -1.0 minus log P saturation. So that's when then they define the Z equal to, so initially Z is nothing but PV by RT. Now they design Z equal to nothing but Z0 plus W into Z1. So if I say that, suppose,
Excuse me, sir.
yeah, go on. Hello.
Sir, how could we write that? Sir, can you hear me?
Yeah, I can hear you.
How could we write that omega equation log PR saturation into SF? Can you explain that
Yeah,
again?
1 second. So basically what they done was, so as we all know that, as I said before, the compressibility factor was designed to get the equation for all the systems, but when they are doing the calculation, they found that okay, simple fluids such as the noble gases are getting the what you call desired values, but not for the complex fluids. So to get the more details about the complex fluids, the Pitzer has developed some in thermodynamics. He has started doing the experiments. He has taken, sorry, yeah, what he has done was, he has taken the values of TR, which is reduced temperature, and he has taken the log PR, and then he started plotting the values of all the experiments for the simple fluids, because he thought that okay, simple fluids are giving good values, and he has taken different conditions which TR and PR, and he found out the what is the values, and then he found out he plot the graph and says that okay, this graph goes through one point, that point is nothing but this point, which is y, and this is x. So now what he has done was, say suppose, so this point here, say suppose, I'm just giving example, say suppose Z equal to PV by RT at log PR equal to -1.0 and TR equal to 0.7. But what about the remaining cases? Say suppose if you take any complex fluids, like suppose N-butanol or N-propanol, this won't go through the this won't go through this line. So then the whatever so that line will go in this different way. That line will go like this. Some may go like this. So what he has done was, okay, this simple fluids, wherever the condition is satisfying, he has taken this line, and how much deviation is happening, that is what he called as eccentric factor. So that's when he said that, okay, I have some value for this is the standard value x, I have standard value which is at minus 1.0, and how much deviation I am occurring, that is y, which is log of p of saturated value at tr equal to 0.7. At this tr equal to 0.7, so suppose if I plot it here, he kept this value as constant. So basically if you see, the equation is 1 by tr, sorry, one second, yeah. So what he has done was, he plotted three graphs. One is the simple fluids, assume this is the simple fluids. It's better I think to draw it down. Yeah, if you take this one, so the physicist has drawn the he has carried out the experiments for simple fluids. Say this is for the N-butanol or some other cases, and this graph is for some other cases. He got different graphs. They have done the experiment for more graphs. So assume this is the main one. So what he has done was, at t equal to 0.7, reduce the temperature. So suppose if you have the T as 300 Kelvin, the critical point is 350 Tc, then reduced temperature will be 300 divided by 350, right? So that's why it will be less than 1 always, because the critical point is the highest point, and whatever the temperature we are dealing, it will be less than the critical point. So the value will be always less than 1. So that's why he has fixed this point, and he has taken that, okay, this is the value which we know, which is minus 1. And for the remaining factor, what he has done was, he had taken, okay, w, eccentric factor, he made eccentric factor, how much deviation it is occurring, so that he minused it. If you see, that's what, minus 0.10 minus x at tr equal to 0.7. So then he used the same factor, the eccentric factor value here, z equal to, this is the z naught plus w z1. Assume that this is a simple fluid where the w naught will be 0. That is the basic condition he has taken. Then w naught equal to 0, then this equation will be basically pv by rt. So then it is also pv by rt, but for that case with the w value. Any doubts regarding this? If you don't understand any point, I will explain it again.
No, sir, got it, sir.
Thank you. I will share, and then you don't. One more thing, there is like in the James Smith book, there is appendix B and I think D. In the tutorial it says that E, it's not E, it's a B and D, where you will get the values of W eccentric factor values, reduced pressure values, and say suppose if I say that I think there is one example problem saying that you have N-butanol value and find out the what you call given using a compressibility factor, find out the values of this and so on. They ask for that enthalpy or something, they ask I think in the example problem. So for that you can go to the appendix B, you can go to the appendix B and D, where you can have the, okay, this is the particular molecule. So I think there is a few n number of molecules with N-butanol or isopropanol, everything. From there you can go from TR, PR and everything, and you can see the values and then the eccentric factor values based upon regarding that values. I think I will share after the class the B and D appendixes. If you're not available, you can just mail me, mail in the group discussion, or I will upload that in the drive folder. So it is very easy one. You will be given the appendix values, what are the TR, reduce the pressure and reduce the temperature, and then you need to calculate the compressibility factor values. So once the compressibility factor is, see, you need to understand that whatever we are discussing in the today's class was like, okay, we have ideal gas equations, and then for real gas equations we have designed one equations, and that equations are deviating from the things. Suppose whatever the real gases we are discussed, that is only applicable for the real fluids, but for the other complex fluids it is deviating little bit. So we are designing the new formulas for deviations. Okay, the main formula is same. So suppose if I talk the compressibility factor, the z equal to pv by rt, or 1 plus whatever we discussed in the previous class, 1 plus bp plus cp square and everything, that will be same. But if you are going for the more complex fluids, what are the new terms which can be added? That's what we are discussing in today's class. So once the compressibility factor is done, what we have is residual properties. one second. Yeah, so residual property. So basically residual so as of now we discuss the compressibility factor. So for if I given any ideal gases, it will be PV equal to RT. For any compressibility factor, Z equal to VB by V ideal gas, and if there is any virial equation, it will go from Z equal to 1 plus blah blah blah, and there is Van der Waal or Redlich-Kwong equation. Redlich-Kwong equation, you know that how the P, V, T and differentiate, and if there are any deviations from it, how to use the centric factor, which is Z equal to Z0 plus W into Z1. So this is the basic things regarding equation of state as a function of P, V, comma T. If you have any two values, how to find out the third value, and this is how for the real ideal gas, how can you do it for real gases, and for the virial equation, and for the cubic equations, and for the if there are deviations, and then how you can use the centric factor. So this is what we discussed in the previously. For now what we are discussing was, so we are discussing for the, okay, I have enthalpy, internal energy, entropy, Gibbs free energy, and Helmholtz energy. So how to design this in a simplest form? So that's what we are discussing in today's class. So we are given the temperature, pressure. Other than that, how can we do it more without any deviation? So that's what we are going to discuss today's class about the residual property. So we all know that, so basic equation says that M residue equal to whatever the original one divided by ideal gas, which is nothing but M equal to M residual plus M ideal. We will do with the example of Gibbs energy. I will write, I think I will make it very small. So if I take the Gibbs energy, one second, I will write the equations first. dg equal to vdp minus sdt, and we will make one as dimensionless method. So we all know that gt equal to RT ln q minus RT ln q, delta g equal to, I'm just writing it for the sake of dimensionless. So we can write for the dimensionless, I will write it like this. So what we'll do is, we'll do the, so for this if you apply d by g by RT, what you will get was, if you use the u by v rule, basically what you will get was 1 by RT into uv rule. So suppose differentiation of uv, just assume that uv is you can write it anyway, uv dash plus vu dash, or u dash v plus v dash u, because here we have the positive sign. So now in that way what I will do was plus, if I take g out, d by RT is minus 1 by RT square dt, it is equal to dg by RT minus g by RT square dt. So I think red is much more better color. So now d of g by RT equal to dg by RT minus g by RT square dt. We already know what is dg. Dg is nothing but vdp minus sdt. So now I will apply this in this. So now it will become d of g by RT. If you see, what we are doing was, we are doing with the dimensionless number, because dimensionless number. So it will be vdp minus sdt divided by RT minus g by RT square dt. And if I take it, so we also know this. So here we are using three formulas, dg equal to vdp minus sdt, g equal to h minus ts, and g by RT for dimensionless number. This is dimensionless. So then now we have g as h minus t. So then this will be written as vdp minus sdt by RT minus h minus ts by RT square dt. If I expand it, it will go like this, will come here itself. So I am not writing that equation again. dB by RT minus S dB by RT minus H by H dt by RT square plus Ts by RT square dt. This T will get cancelled. So this whole equation is same, so this will get cancelled, and the new equation will be so any doubts in this equation, how we got this equation? I will explain it again if you have any doubts. So now we got the dimensionless number g by rt as function of dp by p comma t. So this is another way how we can make, say suppose initially we have discussed the enthalpy and entropy as a function of t comma p. If I given that, can you find out the Gibbs free energy in the, if I given some values and I given the temperature and pressure, can you find out? So this is, and if I given the enthalpy values, and this is the, as you already know, how can you get the enthalpy values from temperature and pressure? You can calculate that, and then you can calculate the g values from this equation, as it is also. Any doubts regarding this equation?
No, sir.
Okay, fine. If there is no doubts, then with this residual properties, there are many more properties to clear. So I will further, so what I will do was, I will make the slides, the plain slides, and we will discuss more about this, and then the fugacity coefficient. One second, just I am making it. So now whatever the equation we are dealing with, so now what is the equation we have dealt? So make sure that I am writing correctly. If it is wrong, just let me know. You guys can hear me, right? Hello?
Yes, sir.
Yeah, fine, thank you. So now we have the dimensionless number g by rt equal to, the equation is v by rt dp minus h by rt square, so dt, and we know from the Maxwell and reciprocation formulas, so we can get v by rt equals to dou of g by rt divided by dp at constant temperature, and minus h by rt equal to, plus h by rt equal to minus t into, so these are the other two important equations. Yeah, fine. So this is the other two equations which we will deal, and so we all know that u equal to h minus pv, so then uv by rt, to get the dimensionless number we'll write like this, uv by rt. Same thing for the Gibbs, g equal to h minus ts, then g by rt equal to h by rt minus ts by rt. Yeah. So you will get s by r equal to h by rt minus g by rt. So once you know that, yeah. So in the last classes we discussed that, say suppose if I, at the constant temperature, say we have taken, at constant temperature I want to find the Gibbs energy at P2 comma T. What is the P2 comma T? From G of P1 comma T. What we can do was, previously what we did was, if you remember in the previous classes, what we taken was G as VdP, so then G2 equal to G1 plus integration of VdP. Then we are taken for ideal gases, what we had done was G2 equal to G1 plus ln of RT by dP by P. Then this will come as G1 plus RT ln P2 by P1. So this is what previously we have discussed. Now the same thing we will do it again. So now I have, but for the dimensionless number, so what we have was, I will take this equation now. Now I will take this equation. So the equation is d of g by rt equal to v by rt dp at constant t, because at constant t this will get cancelled. So now what we have is, so g by rt is nothing but g2 by rt. So I am writing at that pressure p2, it is equal to g1 by rt plus integration of v by rt dp from pressure. And if I take this as a initial condition, so it will be, so if I write it here, if I write it this one as, so this is completed. So now if I write it like this, so then it will be like g residual for the rt, it is equal to at p equal to 0 plus integration of 0 to p vr by rt dp. So if you have any doubts regarding these equations, you can ask me. So now I am making this as a constant value. So as at the ideal at the zero condition there will be constant value. So if I write the constant as a j factor, so then this will become as gr by rt equal to j plus integration of 0 to p vr by vp into dp. Okay, so this is the how we can write the same equation here. Now yeah, so now what we can do is, so if I take this one, now I will take the compressibility factor equation. Compressible, so because here we have the dp and v which is not integrated because there is no term for the integration. So what I will do was, so I will make this is another column. Now what I will take was, we all know that z equal to pv by rt. Now yeah, z equal to pv by rt. So now what we have is, now we all know that vr equal to v minus, so here also vr, right? So vr is, because we initially discussed that initially I have said it here, any factor given vr equal to v minus v ideal. So here it will be like, it will go vr equal to v minus v ideal. So that's what I did in here. So now I am taking the new slide. I'll make the 3 columns, it will be better. So yeah, so now once again, now the camera is gone off. Yeah, so now what we have is, sorry, now what is the equation? gr by rt, sorry, yes, gr by rt equal to j plus integration of 0 to p integration of p vr by rt dp. We know that vr equal to v minus ideal, so we know this is also, so it will be v minus v ideal is rt by pv equal to rt by p, I think, yeah, rt by p. So now what is the equation we have? Now we know this compressibility factor equation, it has zrt by p, because you know that z equal to pv by rt and v equal to zrt by p. So that's what we are writing here, minus rt by p. So now if I take rt by p common, we have z minus 1. Now I will include vr here. So what we will get was, integration of 0 to p rt by p z minus 1 divided by, sorry, once again, rt dp. So this rt will get cancelled. So now we have integration of p. So this is the final equation for the compressibility, given the compressibility factor and the pressure, how to deal with this equation. Any doubts regarding this equation? If there are no doubts, then I will go forward. Once this equation is done, we also know that from the closed systems, yeah, hello,
So can I explain it a little?
okay, I will explain the same from the starting or from, okay, I will explain it again, 1 second.
No, sir, from the condition where you kept the temperature as constant.
From here?
Yes, sir.
Okay, fine. So In the previous classes, if you know, we know that delta G equal to VdP minus SdT, right? So if it is constant temperature, this will get cancelled. So it means dg equal to VdP. So it means G2 minus G1 equal to VdP. G2 means, say, suppose it's already at constant, as we already says that it is a function of G is a function of P comma T, because we are differentiating G with the P and T, and we kept T as constant, so it will be P2 comma T minus G of P1 comma T equal to VdP. This is for the ideal gases, which we discussed in the last classes. So then this will go like G of P2 comma T equal to G of P1 comma T plus integration of, so because we remove the integration, right? So here it will go integration. So integration of P1 to P2 VdP. As this is the ideal gas, this will go RT by P dP. And this is for the ideal gas condition. If I take the standard temperature, which is 1 bar, so instead of writing 1 bar, which we will write as the ideal gas, just not standard, just assume it as a standard. Okay, if I applicable same thing in this equation, so this, what is this equation? One second. Yeah, this equation, one second. So this equation we have is d of G by RT equal to V by RT dP minus H by RT square dt. Now if I write it in the real residual terms, this equation will go as this will be like this. So now if I take constant T, as we all know that gr is a function of, gr by RT is a function of P comma T, because it is a dimensionless number P comma T. Now I kept T as constant, so if there is a T constant, then dt will be 0. So then the what is the equation we have is gr by RT equal to V by R RT dP. So now if I use the same formula here, it will be G of R by RT of P2 comma T minus G of R RT P1 comma T equals to VR integration of P1 by P2 RT dP. Now if I take, we know that from the residual relation, this is the residual equation, so it means we have ideal. So we know that for ideal it is PV equal to RT, then V equal to, this will be RT by P. For the compressible, we have for the normal gases, if it is not ideal, then we have the compressibility factor, which says that Z equal to PV by RT, which goes V equal to ZRT by P. Now I taken RT by P as common, it will be Z minus 1. So now I use VR here, so then it will be like GR by GRT at pressure T2 comma T equal to GR by RT P1 comma T plus integration of P1 to P2 RT by P Z minus 1. So here, as initially we discussed, is standard, so here it is standard, and we coined that standard as a J. So now I coined this term as J. So now the whole equation will go, one second, I need to take new slide. One second, there is a slide issues, internet issue. So now we have the equation is, sorry, I think I didn't write. G by R RT at P2 comma T equal to J plus integration of 0 to P, because we kept this as J as at initial zeroth condition. This will go as Z minus 1 dp by p. Understand this equation now, or any doubts?
Yes, sir, now understood.
Okay, fine. So now we have so initially I have said that we have already discussed that g equal to h minus ts, then g by rt equal to h by rt minus rt. So then s equal to h by rt minus g by rt. So now we derived the equation for this. So the same way we can derive for s by r. The same way we can once again. In the same way we can derive the equations for, if I go through this, yeah. So from the closed system we know the equations of dh by dt equal to cp. If you remember our previous classes, we have written h, sorry, here only I will write h as a function of t comma p and s as a function of t comma p. From there, if you go there to that equation and if you put the dimensionless number there, you will get h as this and ds by dt as cp dt by t minus r dp by p. You can recheck the previous classes. ds by dt equal to cp by dt minus r dp by p. So now, as we already discussed, it will be h by rt equal to, we all know that from today's class, we already understood that it will be dt at constant pressure, and we know that, and we also, so from today's class we understood that h by rt equal to minus t by dt by p, and we have this equation. Then s by r will be minus t of dz by, so this will be ds, yeah, by rt dt at constant pressure. This is for this, and then minus of this equation whole here, that is z plus whatever it is, integration of 0 to p z minus 1 dp by p. Any doubts regarding these equations? We will discuss it again. Is there any doubts regarding this equation? And this equation can be written as s by r equal to minus t integration at constant pressure. So we will have dz by dp dz by dt, and this is at constant pressure, right? So you can't, this will be a constant term, so minus of j minus 0 to p minus z by. So what we have done was, we have taken the same cases of previously what we had done for the closed system for without any dimensionless number. What we have done was, we have taken g, and then we have there we have taken h, s, and then we have gone for g. Here we have taken g initially, and we have done the calculation for g, and then we will go for, we have gone for h and s. So these are the basic equations. I think this is how the sir has derived the equations, and using this equation and using the appendixes, appendix I think E, you can formulate the formulas and you can find out the values whatever they ask the values. If you have any doubts regarding this, I will explain, otherwise I will go further. Any doubts? If you have any doubts?
No, sir.
Okay, thank you. So then we have, I think we discussed the eccentric factor, and we have discussed the eccentric factor. When eccentric factor is basically for the compressibility factor. So whenever I say the compressibility factor, there are any errors for the complex fluids, then we have gone through that. And then once we have the residual properties is basically for the fluids which how to define the fluids with the dimensionless number. And then now we will go for the fugacity coefficient. So fugacity coefficient, so just now we discussed that g2 equal to g1 plus integration of p1 to p2 rt by p2 by pdp. This will give as g2 equal to g1 plus rt into, if I write it in write G2 equal to G1 plus RT ln of P2 by P1. Just assume that P1 here we have taken as a initial condition, which will be 1 bar. If it is 1 bar, then this equation will go as, this is also at 1 bar, so this is the initial condition, it will be ln of P2 only. But for the to get equal terms, here there is one value which is 1, so that you will get, this will be like no units. You need to understand that. So this is for the ideal gas condition. The same thing if it is for the real gases, this equation will become as this one. This is the fugacity coefficient, which we will discussing in the today's class. Yeah. So basically fugacity coefficient. So for the ideal gases, we will get the P2 by P1. For the fugacity, which is as we all know that the chemical potential. Say suppose if I given, I will discuss the chemical potential as the last part of the class. So just for now, just understand this equation. G2 equal to G1 plus RT ln fugacity coefficient of I divided by P1. Assume if it is not the initial condition as a 1 bar standard condition, and then we have this can be also can be written as RT ln phi equal to Fi by Pi. So if I apply limits to both the cases, so now if I apply the same condition to the G2 by RT equal to G1 by RT, which goes to limit phi, it is equal to J limit phi as P tends to 0. If it is P tends to 0, then it could be 0, and then G2 equal to J only, right? Because we have the equation of Z minus 1 dP by P. If you remember, previously we have written this equation. So if this is going to be 0, then G2 equal to J. So that's what I written here. G2 by RT limit P tends to 0, G2 by RT equal to limit P tends to 0 phi, it is equal to, if it is 0, then it will be J. So now then we know that 0 to P Z minus 1 dP by P at constant temperature. So any doubts in this? So this will become as, yeah, so now limit P tends to 0 phi, which means if it is getting 0, then we get log phi log 0, it is 1. E port 0 equal to 1. So now, so this is the final equation for the fugacity. Any doubts regarding the fugacity equation? So ln of phi equal to 0 of P Z minus 1 dP by P at constant T. So this is the fugacity equation. If any doubts regarding the compressibility factor or the residual properties or the fugacity equation, we will discuss. Otherwise, I will move further. Any doubts regarding these three topics? If you have no doubts, then am I audible? Hello?
Sir, how did you arrive that last step? Limit 5 is equal to.
No, it's not limit.
That last
Actually, it's not limit, it's ln.
Okay.
It's ln. It's not the limit, it's ln. The limit comes only up to here. So that's why it's a typing mistake, so that's why I written it here again. Any further doubts? If there are no doubts, then we can go to the chemical potential topic for the brief of half an hour. Just 1 minute. Give me time of 1 minute. Just get it. Yes. So I think in the previous classes, we'll keep this one. So we have few more. We have 20 more minutes. What we can do was I will add this slide there in the class. Okay, fine. I'll add few more slides here. So any doubts regarding the first week to the fourth week assignment problems? We can discuss. If you have any doubts regarding the first week to fourth week assignments, any doubts regarding the first week to fourth week, we can discuss in the next 2-3 minutes. It's okay, fine. Then I think I'll go chemical potential. So chemical potential. So as of now, okay. Before this, we will have the. I think at the end of your week 4, you have the review module. So what in the review module, what they discussed was, we have ideal gas, we have virial equation, we have cubic equation. If any gas is not following this, how can we apply the eccentric factor? That is Z equal to Z0 plus W into Z1, which is deviating from the original one. If you take any if you take any simple fluids, this will become 0. Then Z equal to Z0, which is equal to Z0 is PV by RT. So this is one. And then the next we have the residual property. If I take any equation, say suppose if I take any G VdP minus SdT, and if you can apply as a dimensionless number, and if you solve this equation, we at the end we will get G by RT equal to V by RT dP minus H by RT square dt. So this is another dimensionless form. So these are the week 4 classes. So then for this, what you can do was, say suppose in the isopropanol case, I think one of the example which we discussed in the SAR has discussed was the isopropanol case. So for that, say suppose if I ask to find the compressibility factor, this is also one of your assignment question. This is also one of the model for the assignment question, which question can be asked. Say compressibility factor for the isopropanol at T equal to 200 degrees Celsius and pressure equal to 1.1 bar. We need to go to the appendix B of I think the appendix B will be given to you. If you take isopropanol, it can be written as 2-propanol, which is written in the sheet. So which we can do. So there they given the values for the residual temperature. Why we will do as critical temperature, and the PR is P by PC. So now the residual temperature will be 200 plus 273 divided by critical temperature given at the table. Same thing for the PR. It is the given, suppose it is 1.1 bar divided by the pressure given the critical temperature. So then you will have the eccentric. So then you have the symmetric value, some x. It will be like 0.66, I think. You have the Z0 values, and at the same time you have the Z1. Then you will get the Z0 equal to Z0 plus W into Z1. And if they ask you to find the enthalpy or entropy for the given the, so now you got the compressibility factor value. So then as we already discussed that if you ask to find out the Gibbs free energy, you can do it simply just by Z minus 1P by dPpp. So this is the easiest way you can do. So which is nothing but ln P, that's it, yeah, Z minus 1. So first you can do this and then followed by this. So this is the how you can do the assignment problems. If you have any doubts regarding this, you can raise the question in the forum. So once this is done, we have the now chemical potential. So chemical potential mu, if you see in the previous classes for the open systems, so open systems we are taking say suppose if you take any function, if I take any function, say suppose we will go to the functions. I will take the open system of u comma s comma b comma n. Otherwise I can take the equation of this one also, right? Gibbs free energy, because we are anyways talking about the Gibbs free energy. So if you take Gibbs free energy, dg equal to vdp minus sdt. So there it is for the closed system, g is a function of pressure comma t, but if you take any open system, g is also a function of p comma t comma en, and this equation can be written as, you all know that dg can be written as d of dp at t comma n plus d of p at p comma n plus d of g n at p comma t. So this written as a chemical potential mu I equal to sigma of, so basically here sigma of gi ni equal to gi at the molar volume. So for this there is an equation saying that g2 equal to g1 plus rt ln p, which is equal to mu2 equal to mu naught plus rt ln p. So chemical potential, which is responsible for the chemical equilibrium. So if I take any example, say suppose I have taken some any moisture, you can see some examples, right? If I take any sea from the Antarctic Ocean and kept it in the freezer, it won't it gets spoiled, or it will get burst out. Or if I take any skin molecule, say suppose I have taken a slice of the skin and I put it in the any container. So what is happening was, it try in water container, say suppose, sorry, hello, I'm audible? Yeah. One second, I think. Hello? Hello?
Yes, sir.
Yeah, sorry, I thought there is a slight power off. I thought the connection is gone. Sorry. Yeah, sorry for the lag. So suppose I have taken, I think my pen is not working, don't know why. One second. Okay, for now I'll make it like this. So we have taken any box and say suppose I kept something in the box. Say suppose I kept the skin molecules, what it with the water in it. Just bear with me because my writing pad is not working. Yeah. So now I have taken this one. So what it try was, the skin will try to absorb the water molecules and it will expand. So it will expand in such a that it will burst out. So why it is happening was because the major factor for this was the chemical potential. So how can I say the chemical potential was? Say as we discussed in the first zeroth life, thermodynamics. I'm just correlating with this. It's not entirely the same. What we will do was, the heat is transferred from the hot body to the cold body. Here the same thing. The chemical potential will be moved from the smaller body to the higher body. Yeah. So that's why if it wants to go into that environment. So that's why it will take more of the water molecules and it will get burst out. The same another case was, if you take any example of water in the ice. Say suppose if I keep, why it is not working? It's not working. If I take the case of water, say suppose this is all the water and I kept an ice cube here. Now can you tell me why the ice cube get melted? You can understand, right? So why, if assume that it's not in the equilibrium condition, something has to happen, right? So why the ice cube wants to, because the chemical potential of the mixture is less than the chemical potential of the individual. So that's why it will stay, if I take any critical point, it will stay as it is, because the chemical potential of the mixture will always be less than the chemical potential of the individual. So these things I think we will discuss further in the next classes, and how we can derive the this formula, how the mu2 equal to this formula, how we can derive. I think we will discuss in the next classes. If I given any two gases, say suppose I have taken the two containers where we have, I have taken the two containers where we have the mixture AB and we have only A. and say suppose the chemical potential of the mixture is, as I said now, the chemical potential of mixture is always less than the A. So then the A wants to go, the A wants to move freely. So if A moves freely, so what happens? And the basic equation. So from here, the basic, say suppose the zeroth law used for the temperature and the entropy used for some other things, and this is the best example for the urea development. So how the urea is developed based upon this equation. So they have taken nitrogen and oxygen, sorry, nitrogen and water, and then they mix together and they get the ammonia. So sorry, nitrogen and hydrogen, and they mixed it in the same chemical potential formula, and the mixture has very less synthetically available. So that's why not synthetically available, less equilibrated at the mixture form. So that all the cases we will discuss in the next classes, how the entropy change is happening when, say suppose if I give any reaction, A plus B gives rise to C plus D. Okay, how the suppose if I give any equation like ammonia, nitrogen and hydrogen has mixed and gives rise to ammonia, just understand like this. Nitrogen and hydrogen has mixed and gives the ammonia. If I make it like A plus B as ammonia and hydrogen to give rise to C plus D, how does this equation varies with respect to the, if I say it's not ammonia, it's like another C plus D compounds. Okay, why it is forming ammonia, why not any other C plus D components, and how the entropy will vary. If I take the state variables, say suppose if I take A and B as the starting points and C and D as a end points, and if I calculate the state variables delta G free energy conditions, we'll understand how well it is differentiating. That's all we will discuss in the next classes, as I think next class will be on Tuesday, which we will discuss more about how we will deal with this type of things. And if you have any doubts, it's not about the doubts, and then yeah, I think we have further another, I'll keep it. Yeah, if you have any doubts regarding these things, I can ask me regarding any cubic equations or any other things. I'll explain if you have any questions. Up to fugacity coefficient, if you have any questions, you can ask me. I'll explain it again. How can you calculate the enthalpy and entropy? I will explain it again, that things are how we are using the compressibility factor, or how we are dealing with this, or how can we use statistical thermodynamics in the, as we said, right, the compressibility factor, which is takes the only critical temperature and critical pressure, and there is another term for that. There is another third coin which will do it in the further classes, that is statistical mechanics. When we are dealing with the statistical mechanics, I will blend the third property of along with the critical temperature and critical pressure for the calculation of compressibility factor. That we will discuss in the later part of the course. And I think up to 4th class, I think what are the assignment questions we have as a what do you call problematic. I think using these formulas, and you can solve it easily. And after the class, I will share the appendixes, appendix I think B and D. And if you want any, the today's class is followed from the James Smith chapter 3, I think chapter 3 and 10 and 6. So these 3 chapters covers the residual property, generalized correlations of ideal gases and virial equations, and the chemical potential also. And if you want to and you can do, there are some nice example problems where you can use, say suppose they ask to figure out what will be the values, and you can try that examples. And if you have any doubts or queries, you can ask, or you can raise the questions regarding that queries. And yeah, if you have any doubts regarding this session, you can ask. Any doubts?
Sir, last week I asked you about
critical
the
temperature. Yes.
assignment.
Yeah. One second. I'm stopping screen the share so that I'll open the screen. Okay. 2 seconds. 1 second. I will open the. I think I didn't save it. One second, just I will open the question. Then we'll come back. That question they say they given that, right, for the nitrogen they have used the PT case. Out of the PT they said that I think a point is one point is critical point. I think you have kept the right answer. And they said that the second third option is the changes from A to B with respect to the increase in pressure, and that's what, right? What is your doubt in that question? Can you explain me the doubt? Hello, hello, can you hear me? Hello, I think I'm on.
Yes.
Yeah, can you explain me the doubt what you have in that question? I just read the question. I think I can't use my notepad. So basically in that question what they said was they are going from one point to another point. You need to remember that if you take any triple point cases, there they given the three cases. One is PT case, liquid, solid and vapor region, if I am not wrong. When you are going from point A to point B, it is inclined with the increasing pressure, and you can, I think the temperature also. I think there are multiple choice question, right? It is. So I think I don't know what is your doubt in that question. If you can explain me your doubt, I will explain it clearly that question. The PT surface. Okay, the PT surface I will make it in the next class. I will explain the concept again, and in the next Tuesday class I will explain the first the PT surface and PV surface. Along with that we have the PVT surface, the three diagram. I will explain this, and then we will see some examples along with the assignment question. Okay, in the next class.
Okay, sir.
I will explain clearly that what is PT surface, how the values are changing, and how the critical point is obtained. I will explain this in the next classes. Okay.
Okay, sir.
If you have any doubts regarding any theoretical or problems, you can let me know up to week 4. I think week 5 also the same concept. We have the chemical potential. I think I have briefly explained the chemical potential concept. If you have any doubts up to week 4 and off, I think so, you can ask me. If you have any questions. If there are no questions, then I think week 4 is enough. So if you have no doubts, you can leave the class. If there are no doubts. If there are no doubts, thank you for attending the class. Hello.
Sir, can you explain Jacobian method once more?
Jacobian once. One second. I think we discussed. Yeah. So what does the Jacobian do was, one second. I think I will close the screen. Can you see the screen? I will explain briefly. In the next class, I will make it the PPT version of Jacobian. Okay. So what is happening was, suppose I want to find h of t comma p and s comma p as a enthalpy and entropy. So I will take so yeah. So what in the Jacobian what he's taken was, he has taken the how to do it. The Jacobian will write it in this format. If I say, if the equation y, say suppose if there is any x is a function of a to b and y is a function of c comma d, then Jacobian will be written as, I think I will write it here. The Jacobian will be written as dx by dA dx by dv, the same way as then dy by dA, sorry, dy by dA, and then same thing for the dy by dv. So then he will apply the matrix rule. In the Jacobian method, what we will do is we will apply the matrix rule such that AD minus BC, and that's what we have done here. So if I apply AD minus BC and then dx by dA into dy by dv minus dx dv by dv by dx, so then we will differentiate from there. So the writing pattern, I will explain PVT surface and Jacobian method in the classes where to say that how to solve it with better example. Okay, in the next class. I think I not prepared the PPT, and the writing pad is also not working well. So yeah, basically Jacobian, what he will do, not what we will do in that method was, as Maxwell, what we will do was, in the same method we will do in the Jacobian, what we will do was, say suppose h is a function of t comma p, s is a function of t comma p, we will write dh by dt and dh by dp. The same thing for s of t comma p as ds by dt and ds by dp, and then he will take the matrix form and then ds by dt into dh by dt. So I'll as I mentioned it here, he will do it in this format, and then from here he will solve it. I will explain it in the next class with further good examples. Any other doubts? I think there is a concept clear for the van der Waal, and you can see if there is in the future for the van der Waal. I think 1 second I will explain. I thought I can share something for the. So there are n number of equations for the van der Waal. Say there are n number of people who has done for the equation of state for the PVT. Initially the van der Waal has done for the equation, as you know, that v square, where we are checking the attraction repulsion between the two molecules, and then further we have seen the Redlich-Kwong equation, and there are Smith equation also. If you refer the James Smith, it will be better to understand that okay, what is the advancement in the cubic equations of the state equations. Okay, just go through the James Smith. If you're not getting any James Smith, I will upload. If you want, I will upload the book in the drive folder. If you are unable to get the book, and I think in the last class, I think you have the doubt regarding how to calculate the entropy and enthalpy. I think this question. Have you get this one? Which one it is? I think not this one. I think this one. Yeah. Have you got this one? How to do it? Hello. Hello. Am I audible? Is anyone? Yeah. I think Fahima, you have a doubt, right? In the last class, how to calculate this m into, if I given any saturated steam and steam under various pressures, various conditions, we need to go to the appendix E and we searched it. M equal to m into x2 minus x1 divided by x2 minus x by x2 minus x1 into m1 plus. Have you figured it out? If not, then it is.
Yes, sir.
Yeah, thank you. If not, then it is a drive folder. You can the same PPT will be uploaded in the drive folder also. If you have any doubts regarding this, you can check it out there also. Yeah, any further questions about this? So if you ask any problem, you need to remember either Maxwell or Jacobian to figure out that what is G equal to H minus Ts, or S equal to, how can we explorate the functions of enthalpy, entropy, free energy and Gibbs energy. So as of now we discuss up to now we discuss like it is the midway of the classes, like we have completed I think 6 classes in the 6 weeks course. As of now we discuss what is the temperature and how the zeroth law works, and the internal energy and the second law of thermodynamics, entropy. And the next class I will I think I will explain more about the chemical potential and the Jacobian method and surfaces diagrams. I will revisit the surface diagrams, and then after chemical potential we will go further into I think what is the then 6th week course, week 6. Have we gone through the week 6 course? Up to week 5, no, there is a chemical potential and there are Lewis rule, Land rule. I will explain all the courses in the I think Tuesday class most probably, and this week it's been delayed to the Saturday, and sorry for this. Yeah, if you have further any questions you can ask. Any questions regarding interest in thermodynamics, how the thermodynamics is applicable? About chemical potentials and the Fugacity coefficient. Fugacity coefficient is mainly for the real gases. For the ideal gases, if I take the two conditions, okay, at the equilibrium, the pressure and temperature at the constant temperature, if we followed the Gibbs energy, and this will be the cases. And for the further, it will be that if I take the real gases, that ideal gas condition ln P2 will go to the ln Fi, and by applying the limit tends to 0, where the ln P will goes to the e power 0, which comes to the V, which which can be further discussed in the factors of compressibility factor. And if you have any doubts regarding this session, you can refer SAR Pro notes, as SAR is explained much better with the examples. And further, if you have any doubts, you can go through the James Smith, or there are 3 to 4 books which you can refer. And the best important the coursework is James Smith. And either if you have any questions, you can raise the questions in the discussion form. We will discuss it further. And thank you for attending the class.